Welcome to part 4 of our lecture video series from Monday, May 1st, where we look at pressure relationships to other physical properties of a gas, namely things like its temperature, volume, moles, etc. So let's get into it. So I kind of already gave this away like 5 seconds ago, but let's see if we can't answer this question for ourselves. So the question is, what conditions affect the number of collisions in the sample of a gas? And I want to remind us that according to kinetic molecular theory, the source of these collisions, right, or the results of these collisions, I should say, is that we've got forces applied over some area, meaning that we've got some pressure. So according to kinetic molecular theory, the number of collisions is what gives rise to some proportional amount or change in pressure. So if we increase the number of collisions, then we are increasing the pressure. That is what this little proportionality means in general. One trend follows the other. And we're actually going to get into this a little bit more. I know we've talked about this before, but I do want to go over this in detail coming up. But for now, let's see if we can answer this question for ourselves. So what conditions could affect the number of collisions? So remember, our collisions are really based on the kinetic energy of our gas particles. So another way of thinking about this is what can affect the kinetic energy of our gas particles. So let's start by thinking about kinetic energy changes. So things that will affect the kinetic energy. These are things like temperature, right? That is one of the assumptions that we make in our kinetic molecular theory, which is that the temperature of a gas sample is directly correlated to the amount of kinetic energy on average that each gas particle has. But that's not the only way to affect number of collisions, right? Of course, if we have particles that are moving much more faster, then the statistical likelihood of those particles encountering one another and thus colliding is higher. However, that's not the only way to get particles to encounter one another. So things that affect the likelihood of a collision happening. Okay, this is something like volume, because if I have a smaller amount of space, that's going to affect how frequently I have an incident of collision. Also, the amount of gas, or moles, N of gas, that's going to affect the likelihood of a collision, right? If I have more things in a sample that are moving around, then the likelihood they're going to smack into one another is going to increase. And let's see here, temperature, volume, moles, I think that's it for us. So in other words, temperature, volume, and moles, since these all affect the number of collisions, they also all in turn affect, I promise I can speak English sometimes, pressure. So let's think about these pressure relationships. And in order to do that, I want us to remind ourselves about the mathematical structure of a proportionality. So how specifically do things like moles, volume, and temperature affect pressure? Like in what way? If I had to describe this with some kind of function, like mathematically, how would I describe their relationship? And the answer to this is these are all via some kind of proportionality. So we have seen up here, right, a direct proportionality. This means that a change in kind of one variable results in the same change in the other. So an increase in one results in an increase in the other. Or a decrease in one results in a decrease in the other. And remember, a direct proportionality is something that is modeled by a linear function. So linear function, y is equal to mx. Again, this is the proportionality constant, slope m. So if I'm looking at the structure of what relates to directly proportional variables, I'm looking at their quotient equal to a constant. This is what it means to be directly proportional, where direct proportionality shows that a change of one type in one variable, so like a change in our dependent, x, is going to result in a similar change in our independent results in a similar change in our dependent. So you can think about this as if I increase x, then I'll increase y, or if I decrease x, then I'll decrease y. That is what it means to be a direct proportionality. This will be modeled by a linear function. The other type of proportionality we have is an inverse proportionality, where we have kind of the opposite trend of our direct proportionality. So this is where we see opposite changes as the result of changing one. So if I change my x, then I see an opposite trend in y. And if I were to write this mathematically, instead of having my quotient, so inverse, remember that's something over something else, this would be y over x is equal to m. This is what an inverse is. So this is the inverse here. Let's see here. Am I doing this correctly? No, I am not. Can we do basic math today? Don't think we can. All right, let's work backwards, Professor Cadlin. X times y is equal to a constant. There we go, which means that y over m is equal to x. And this is our inverse relationship here. Okay. Main idea is the mathematical structure of this inverse relationship is one where we have a product of our variables equal to a constant. And as a result of one thing changing in one manner, we see an opposite change in the other. So we're going to use this direct and inverse language to think about how things like moles, volume, temperature affect pressure, and then also how these things can affect one another. So let's start with pressure and volume. So let's ask ourselves, as we increase the pressure of a system of gas particles, what happens to the volume? So I think this is really best illustrated by something that we've probably done at the end of a birthday party once in our life, where we take a balloon and we exert some kind of pressure on it by squeezing it. And after exerting that pressure, we see that our volume compresses. So we have a smaller volume of our balloon until we have pushed it so much that our balloon pops. So the balloon popped under pressure. But right up until this popping point, we saw that as we kept pushing and pushing and pushing, or increasing that push, that pressure, our volume decreased. So we see that volume decreases. So if we see an increase in pressure, then we should see a decrease in volume. And if I do this in the reverse, I could say that a decrease in pressure will allow an increase in volume. You could think about this in terms of like, I don't know, wearing really tight pants, right? The second that you unbutton those super constricting pants, right, the volume of your body kind of relaxes outward, increases. And since we have this opposite trend here, this means that we have a inverse proportionality, which means that the product of pressure and volume, so P times V, is equal to some constant. And because P times V is equal to some constant, I could also say that the pressure of our system at some initial condition times the volume of that system at some initial condition is equal to the pressure at some new condition, meaning P1 V1 equals P2 V2 because all of these products are equal to a constant. This is what's known as Boyle's law. So congrats, we just, by using kind of basic logic, derived something that was Boyle's main gig. Do I really care about you knowing these guys' names? No, I don't. But I am going to say them at least once. All right, so we've got Boyle's law. Pressure volume is constant, meaning they are inversely proportional. Okay, what I want for this drilling to stop in my house. I still don't know if you guys can hear it. But what I want you guys to do is I want you to see if you can answer this question for yourselves by kind of going through each of these different options about how can pressure be affected by volume, or how are pressure and moles and pressure and temperature? What about volume and temperature? Think about how all those things are related. So we'll come back and we'll finish this conversation on Wednesday the 3rd. So try to give this a think. Ask yourself, like, what would these relationships be? Would they be direct or inverse? And then we'll do this together on Wednesday and then kind of bring all of our thoughts about this together into one big relationship that relates every variable, pressure, volume, temperature, and moles for some gaseous system. So this is going to be it for Monday, May 1st. We'll continue on the 3rd, and I will see you tomorrow in lab where we do our specific heat lab and we get to do some calorimetry. So see you then.